Picture a single star, lost among 10 million others, packed into a ball of light so dense it looks like one glowing point from Earth. For more than 20 years, that one star kept drifting off course, tugged very slightly, again and again, by something nobody could ever see. Have you ever wondered how scientists can prove something exists without ever detecting a single photon of light from it? A black hole does not glow, does not reflect starlight, and does not show up in any ordinary photograph. What it does do is bend everything around it, warping space itself and pulling on anything that strays too close. So astronomers have learned to hunt for the fingerprint a black hole leaves behind, rather than the black hole itself. That fingerprint is motion. If a visible star is quietly circling an empty patch of sky, something invisible and heavy must be sitting right there. To understand why this particular discovery took 23 years, you first have to understand the neighborhood where it happened. Scattered around our galaxy are roughly 150 ancient balls of stars called globular clusters, some of the oldest structures the Milky Way has ever built. The biggest and heaviest one by far is called Omega Centauri, a cluster so bright it was cataloged as a single star by ancient astronomers, long before anyone realized it was actually 10 million stars crammed into one spot. It sits about 17,900 light-years away, and it is old. Most of its stars formed over 12 billion years ago, back when the universe itself was still young. Here is where it gets interesting. Massive stars do not live forever. When they run out of fuel, the biggest ones collapse under their own gravity and become black holes. A cluster as old and as massive as Omega Centauri should have produced an enormous number of them over its lifetime. Current models put the number at around 10,000 black holes hiding inside its core alone. 10,000 invisible objects, supposedly packed into one relatively small region of sky. So here is a question worth sitting with for a second. If there are really that many, why had astronomers never actually found one? It is not for lack of trying. Deep radio surveys have scanned that cluster. X-ray observatories have stared at it for hours. Spectroscopic surveys have measured the velocities of hundreds of its stars. And for decades, all of that effort turned up exactly 0 confirmed stellar mass black holes in Omega Centauri. In fact, across every single globular cluster in the entire galaxy, only 2 stellar mass black holes had ever been confirmed at all, both inside a completely different cluster called NGC 3201, found back in 2018 and 2019. Those 2 were found using a technique called radial velocity, watching a star's light stretch and squeeze as it swings toward and away from us, tugged by an unseen partner. It works well, but it has a blind spot. It struggles to catch orbits that take a long time to complete, and it needs a fairly bright star to get a clean reading in the first place. If a black hole is paired with a fainter star, or locked into a slow, wide orbit that takes decades rather than days, radial velocity searches can miss it completely. So a different approach was needed. Instead of watching a star's light stretch and squeeze, why not just watch exactly where it sits in the sky, year after year, and see if its position ever curves? This method is called astrometry, and it demands an almost absurd level of patience. You need the same patch of sky photographed over and over, for years, sometimes decades, before a subtle curve in a star's path becomes undeniable. As it happens, one cluster in the galaxy already had exactly that kind of dataset waiting to be mined. The Hubble Space Telescope had been quietly photographing Omega Centauri for more than 20 years. Hundreds of individual exposures, stacked into one of the deepest time-lapse records ever built of a single patch of night sky. That same dataset had already produced one enormous surprise. In 2024, astronomers used it to find evidence of an intermediate mass black hole sitting at the very center of the cluster, thousands of times heavier than the Sun. So this was already known to be a cluster, with at least one monster hiding inside it. The question was whether the ordinary stellar mass black holes, the ones from dying stars, were hiding there too, and whether the data could catch them. To sharpen the picture even further, astronomers added brand new observations from the James Webb Space Telescope, taken in 2024 and 2025, layering the newest, crispest images on top of 2 decades of Hubble history. Combined, that gave them a baseline of 23 years to comb through, hunting for any single star out of millions whose path across the sky refused to be a straight line. And they found one. An ordinary star, not especially bright, not especially unusual, sitting at the exact point in its life where a star begins running low on the hydrogen fuel in its core. Nothing about that star on its own would ever have made headlines. What made it interesting was the shape of its journey across the sky over more than 2 decades. Instead of drifting in a straight line like its neighbors, its path curved, again and again, in a way that only makes sense if something with real mass, but with absolutely no light of its own, was quietly pulling on it the whole time. Think of it like watching one dancer spin in the dark, tracing wide loops around an empty space, and realizing the only way to explain that motion is an invisible partner standing right there, holding on. So what could that invisible partner actually be? Ordinary stars glow. White dwarfs glow faintly. That rules them both out immediately. That leaves 2 real candidates: a neutron star, the ultra-dense leftover core of a different kind of dead star, or a black hole. Here is where the numbers start doing real work. The heaviest neutron star ever measured with real precision tops out at about 2.08 times the mass of our Sun. Go much heavier than that, and physics says it can only be one thing. Astronomers also checked whether this invisible object was quietly feeding on gas from its companion, which would make it glow in X-rays or radio waves. Deep radio scans of that exact spot came back with nothing. Deep X-ray scans came back with nothing too. Whatever this thing is, it is not eating, not glowing, not giving off a single clue in any wavelength we can detect. So picture the full situation. An object heavy enough to rule out every known type of star, completely dark across the entire spectrum, patiently orbiting a normal star for decades on end. So what actually happens the moment astronomers finally catch one of these completely silent, completely invisible black holes red-handed, after decades of searching for exactly this? In 2026, a team led by astronomer Matthew Whitaker at the University of Utah published the answer in the Astrophysical journal Letters. Using 351 separate Hubble exposures spanning 26 years, combined with the new James Webb data from 2024 and 2025, they modeled the star's orbit down to exact numbers. The invisible companion they calculated weighs 46 times the mass of the Sun, comfortably above any known neutron star and squarely inside black hole territory. The orbit itself takes 94 years to complete, stretched into a wide, elongated ellipse with a semi-major axis of 31 astronomical units, making this the longest period black hole binary ever confirmed, anywhere. The visible star weighs about 0.78 times the mass of the Sun, and the whole pair sits roughly half a light year from the exact center of the cluster. The team even calculated the odds that this was all some kind of statistical fluke. The chance of that turned out to be about 1 in 10,000 trillion, which in astronomy is about as close to absolute certainty as it gets. They named it Omega Cat BH2, and it became only the 3rd stellar mass black hole ever dynamically confirmed inside any globular cluster in the galaxy, and the very first one ever caught using this astrometric wobble technique. Here is the real twist though. Everyone expected a black hole born in an old, metal-poor cluster like this one to be heavy, somewhere in the range of 20 to 40 times the mass of the Sun. Instead, this one came in under 5 solar masses, and so did both of the black holes found earlier in NGC 3201. 3 for 3, all surprisingly light. That is a real puzzle, because gravitational wave detectors keep finding much heavier black holes, some over 30 solar masses, merging with each other elsewhere in the universe. Something about how these objects form may need rethinking. The team's simulations also suggest this particular pairing is not primordial. It likely formed through a chance dynamical encounter deep inside the crowded cluster core, and it will not last forever. Because the binary is only loosely bound, a single close pass by another star could eventually rip it apart, most likely sometime within the next 800 million years. The story is not finished yet either. James Webb is scheduled to keep watching this same patch of sky through 2027 and 2028, which should narrow the remaining uncertainty on both the orbit and the exact mass. And the researchers behind this discovery believe the same patient, decades-long method can be pointed at other dense star clusters across the galaxy to find more of these invisible black holes hiding in plain sight, waiting for someone to notice the wobble.